Today's professional learning is going to be all about routine word problems. Within our Spiral instructional platform, today's content on routine word problems will fall under our problem solving category. We have routine word problems and we have directive word problems. Today, we'll be focusing on routine word problems. And those are problems with which students have to identify what information in the story is unknown and how to solve for it. And these routine word problems can be categorized by 5 schemas. And schemas are another way for saying word problem types or structures. And those schemas are total, difference, change, equal groups, and set or comparison. Routine word problems are different from directive word problems. Directive word problems are those word problems that we see on STAR oftentimes that direct students to complete a mathematical task. And directive word problems cannot be categorized into those 5 schemas, which we'll talk about shortly. So this is one example of a directive word problem. It says Yolanda wrote a number. The digit in the millions place is an 8. The digit in the thousands place is a 6. The digit in the hundreds place is a 2. Which number could be the number Yolanda wrote? So in this directive word problem, students are being directed to choose which of those numbers has the correct digits in the specified place value positions. Whereas for routine word problems, students have to interpret a story, determine what is unknown, and then solve for it. All right. So this is an example of a routine word problem. It says tickets for a play were sold on Monday, Tuesday, and Wednesday. If a total of 900 tickets were sold for the play, how many tickets were sold on Wednesday? So in the chat, I want you to share, what do students need to know in order to solve this problem, and what might cause difficulties for students? So these are some of our word problem challenges. Word problems are super complex, and it can be easy as an educator to get frustrated with how difficult word problems can be for our students. And so taking the time to reflect on how complex and demanding word problems are can help take a little bit of pressure off of us and give both ourselves and our students a little more grace. Word problems are tricky, and we hope that the strategies that we teach you today will help your students be more successful moving forward. But some of these difficulties are reading the problem. Oftentimes, students have reading difficulties, and it makes accessing the text of the word problem difficult from the get-go. Students also have to understand the vocabulary in the word problem. They have to identify the important information and ignore any irrelevant information that has been incorporated in the word problem. Often, students have to know how to read charts and graphs. They have to make a plan. They have to solve according to their plan, and then they need to check their work and assess for reasonableness. So word problems, they bring students a lot of challenges. And we're going to talk about 2 strategies that we hope that after this professional learning, you will avoid. And the first strategy is tying keywords to operations. And we understand that it's a very popular and widespread strategy. And I understand why it is, because especially our students with reading difficulties, when we give them this strategy to find a word that they recognize and then choose their operation based on it, it can create an illusion that they are successful in solving the word problem. However, when students search a word problem for a key word and fixate on that key word that is tied to an operation, they don't always read the entirety of the problem. They don't always comprehend the entirety of the situation. And most importantly, for every time that a key word will derive a correct answer, there's an example for when a key word will derive the incorrect answer. So one example is this word problem here. Adriana has 8 fewer students than Candace. If Candace has 18 students, how many students does Adriana have? So in the chat, what is the key word that we see in this word problem? Which of those words might we see on a keywords poster in a classroom? Fewer, absolutely. And so if a student is taught fewer means to subtract all the time, no matter the context, then in this problem, they would be correct. 18 minus 8 has a difference of 10, and Adriana has 10 students. So this is an example where the keyword strategy is successful. However, the word problem underneath it, we have Adriana has 8 fewer students than Candace. If Adriana has 18 students, how many students does Candace have? And so if this student were to subtract for this problem, they would not have the correct answer, and they would not have a holistic conceptual understanding of the word problem. And so I'm going to show you a few more examples. And these are just several examples of keywords posters that teach students that the word together always means to add, or the word each always means to multiply. And this is what we want to try our best to avoid. And the rest of this professional learning will be about replacement strategies, because I know in education, it can be frustrating when you're told what not to do and you're not given replacements for what we should do and what does work based on research. And so hopefully you'll be able to get both during today's professional learning. And so here's another example of a time when the keyword works and another time where the keyword does not work. So up top, we have Cynthia has $70 more than Trisha. If Trisha has $50, how much money does Cynthia have? We see the words more than. If the student were to add, in this example, they would get the correct answer. However, like I said, every example with which a keyword would derive a correct answer, we can find an example of when a keyword would throw a student off and they would not have a conceptual understanding of the word problem or be able to solve the word problem correctly. So this other example is Cynthia has $70 more than Trisha. If Cynthia has $120, how much money does Trisha have? And so in this example, if the student were to add, they would not derive the correct answer. And then just one more example for you. Cynthia wants to share, which oftentimes is associated with division, 36 brownies equally with 6 friends. How many cookies will each friend receive? Well, if this student were to divide, they would be able to get the right answer. But let's look at this other word problem. This one says, Cynthia baked 36 brownies and shared 16 brownies with friends. How many brownies does Cynthia have? So in this example, if a student were to see the word share and divide, because they were taught that share means to divide, they would not be able to solve the word problem correctly. Because rather, when we say share in this word problem, we're saying that Cynthia is giving those brownies away to her friends. So we know that students need to understand keywords. They need to understand vocabulary. They need to understand language, but keywords should not be tied directly to operations. We want to unpack vocabulary for students. We want to make sure that they understand what the words mean in the context of the word problem, but we don't want to say that any word always means to add, subtract, multiply, or divide. And Sarah Powell, our principal investigator for Spiral, she actually did a word problems analysis, and she found that for multi-step word problems, students who use the keyword strategy are accurate less than 10% of the time. So it may seem with these single step word problems that keywords can sometimes derive the correct answer, but when we start introducing multi-step problems, students will be accurate less than 10% of the time, and we want to serve our students better. And so try moving forward not to tie keywords directly to operations. We also want to urge you not to present problems by their operation. And so we see on this worksheet, it says word problems, subtraction. And so if a student were to be handed this worksheet, they wouldn't even need to read the word problems in order to know what equation to write and then solve. It's okay for students to practice isolated subtraction equations, practice isolated multiplication equations. But when it comes to word problems, we want students to always first read the word problem, understand the word problem, and make a plan to solve. If we're telling students up front what operation is necessary to solve the word problem, they won't engage in that deeper thinking and they won't create a conceptual understanding of the word problems. So here's another example, long division word problems. And if you have worksheets like this that you typically use, all you have to do is cut off that header. And then without telling students ahead of time that they are division word problems, have them read them and determine the necessary operations themselves. And so to help students do that, because it's really difficult to read a word problem and understand it and determine what operation you need to use to solve, we have two evidence-based strategies. That is the use of an attack strategy and teaching word problem schemas. And so the attack strategy that we will model for you today and that we have resources for with Spiral is the UPS check attack strategy. And for the rest of this professional learning, I'm going to walk you through UPS check, and I'm also going to walk you through how to solve total difference, change, equal groups, and set or comparison problems. But before I get into it, I want to say up front that we don't expect you to be experts at the end of this professional learning. It's going to be a lot of content, and that's why we have our coaches here to support you. We have videos that model how to solve word problems that fall into each of these schemas. We have activity guides in your binder that helps walk you through how to teach students to solve word problems based on schemas. And your coaches are here to support you every step of the way. So I may move rather quickly through this professional learning, but just know that we have a ton of resources to support you at the end of this professional learning and moving forward. All right, so attack strategies. An attack strategy is a generalized process for working through a word problem. And attack strategies are helpful because they teach students how to problem solve, and they give students a reliable list of steps that they can follow to solve a problem. So whenever they see a word problem, instead of feeling worried or stressed or anxious about where do I start, they can write the attack strategy down on the paper and then follow those steps systematically. Now, there's not one right attack strategy to use. There are a lot of attack strategies out there. However, there are two things that I want you to look for when you're searching for the right attack strategy for your class. And that's that your attack strategy should always start with reading the problem. And if it has a mnemonic, that can make it easier for your students to remember and easier for them to transfer when they're working independently and moving throughout the grade levels. So UPS check stands for understand, so read and explain your understanding. Plan, how will you solve the problem? Solve, set up and do the math. And check, does your answer make sense? And as I model solving word problems for you today, I will model using UPS check. We have tons of resources available for you. We have a video on how to use UPS check, and we have an activity guide in your notebook all about how to use the UPS check attack strategy. And so now we'll launch into teaching word problem schemas, and this is where we're going to use our printable if you have it ready. So schemas. A schema is a foundational understanding of a word problem. And there are other words for schema, such as structure or problem type. There are several common schemas that represent many word problems: total, difference, change, equal groups, and set or comparison. Within schemas, it's important to explicitly teach each of them. And when I was in the classroom and when I was first introduced to schemas, I had to ask myself, are schemas for the teacher to be aware of, or are schemas for the students to be aware of? And y'all, it is so powerful when you explicitly teach students about schemas. And I've found that it gives them this vocabulary that they didn't have before to explain their understanding of word problems and the relationship between the numbers and the word problems. And so schemas and that language of this is a total problem, this is an equal groups problem, it's really powerful when we give it to students to run with. And so within teaching schemas, we want to use multiple representations and precise language to facilitate understanding. And we want to provide our students with ample practice with each schema individually, as well as opportunities to distinguish among the schemas. So to read a word problem and determine which of these schemas does this word problem fall under. And we have, like I said, a demonstration video for each of our schemas, as well as a printed activity guide for each of our schemas in your Spiral Educator notebook. So we're going to start today with additive schemas. And by additive, I mean word problems in which students have to add or subtract in order to solve for the unknown. And so our additive schemas are total problems, difference problems, and change problems. So what is a total problem? A total problem is when we put parts together into a total. And so on this snapshot of your schema poster from Spiral, we see the graphic organizer for total problems, where the total amount can be separated into two parts and the parts can be put back together into a total. And we have what we call a meta equation. And the meta equation for a total problem is P1 plus P2 equals T. P1 stands for part 1, P2 stands for part 2, and T stands for the total. And I'm also going to gesture throughout my explanations of our schemas. Gesturing is when you use your hands to model the actions of the word problem, and we'll watch a video later on that's all about gesturing as well. So let's look at a star example of a total problem. It says Ethel and Gustavo ordered a pizza for dinner. Ethel ate 1/4 of the pizza and Gustavo ate 3/8 of the pizza. How much of the pizza did Ethel and Gustavo eat? And so in this problem, students are asked to combine the part that Ethel ate and the part that Gustavo ate to find the total amount of pizza that Ethel ate. And we have another example of a total problem from the 4th grade math paper sampler from the state of Texas. And it says the owners of a business rented 4,506 and 2/300 square feet of space in an office building. They plan to use 281 and 6/10 square feet of the space for the kitchen. How many square feet of space is left? And so total problems can have the total unknown, and total problems can have one of the parts unknown. And so in the chat, what is unknown in this word problem? Yes, thank you, a part. So this word problem tells students the total amount. It tells students one of the parts. Students have to solve for that missing or unknown part. All right, so now I'm going to walk you through how we can use the total meta equation as well as the UPS check attack strategy to solve this total problem. And then afterwards, I'm going to turn it over to y'all so that you can practice solving a total problem on your printable. So this total problem, before we even read it, we will write our attack strategy down the side of the paper, UPS check. And that's so that students can have a visual reminder for each of the steps of the problem solving process, and they can check those steps as they go as a metacognitive guide. So U stands for understand the problem. And we have to do that. We have to read that. We have to read the word problem to understand it. So this word problem says, Megan baked 28 sugar cookies and 24 chocolate chip cookies. How many cookies did Megan bake in all? And so I always like to ask students, do you understand the problem or do you want to read it again? Do you want to hear it read to you again? Do you want to draw a diagram to better understand the problem? You want to use that opportunity to make sure that students have really thought through the problem and they understand what it's asking. And then we also want students to underline the label. And the label is, what is the word problem asking you to solve for? And in this problem, it's asking about how many cookies Megan baked in all. So the student would underline cookies as their label. And then we can check off the U. Next, we move on to P for plan. And we know that this is a total problem because we have to put the sugar cookies together with the chocolate chip cookies to find the total amount of cookies. So we will write our total meta equation, P1 plus P2 equals T. Then we are able to start filling in our amounts from the story. And like I said, sometimes total problems can have a total that is unknown, and other times total problems can have a part that is unknown. So in this example, we've used a question mark to mark that the total in this story is unknown. We know one of the parts, the 28 sugar cookies, and we know the other part, 24 chocolate chip cookies. And you'll notice that I've checked off those numbers as I've used them in an equation. This is particularly helpful for multi-step problems with 3, 4, 5 numbers so that students can help keep track of the numbers that they've used in their equation. So now we'll write the signs. Those parts are put together into a total, so we need to add. So we're solving for our missing total. We know that 28 plus 24 equals 52 cookies. So we can check off the S for solve. But we also want to check our work. So we'll double check 28 plus 24 does equal 52. And checking your work can look different depending on your word problem. Sometimes it might mean solving the problem again to double check. Sometimes it might mean solving the problem using a different computation strategy. Other times it might mean checking for reasonableness. Well, if Megan had 28 sugar cookies and 24 chocolate chip cookies, then I know that my total will be greater than both of those amounts. And so combined 52 cookies is reasonable. And so I have checked my answer and I am ready to move on. All right. So now I want you guys to try. Please take your printable out and don't forget to write down the UPS check strategy down the side of your paper. I have the meta equation there for you as well as the graphic organizer if you'd like to use that. And this word problem says, a banana farm received a total of 12 millimeters of rain in March and April. If 11 millimeters of rain fell on the farm in March, how many millimeters of rain fell on the farm in April? So go ahead and take a few minutes to solve through this problem the way that you would model solving it for students. So I'm going to go ahead and show you how this problem could be solved using the total equation. So our label answer would be millimeters of rain. And so we've read and understood the problem and we've underlined the label. So we can check off the U. Our total equation is P1 plus P2 equals T. So we will write that on our paper. Our total is the 12 millimeters of rain in March and April combined. So we will write 12 underneath the T for total. We know that part of those millimeters were in, let's see, March. So 11 in March, so that can be P1 for part 1. And then P2 is what is unknown. How many millimeters of rain fell on the farm in April? And so once we write our signs, our equation will say 11 plus blank is the same as 12. So we have to solve for that missing amount. And in this example, our unknown part is 1 millimeter of rain. And when the numbers are larger and further apart than 11 and 12, when students are solving a total problem with a missing part, what they'll need to do to isolate that unknown value is start with the total and subtract the part that they know so that they can figure out the value for that missing part. All right, so we've solved it. And now we're going to double check our answer. We're going to check for reasonableness. And then we can check off that final step of UPS check. So as a review, total problems are when we put parts together into a total. Sometimes the total can be unknown, other times one of the parts can be unknown. And I also want to draw your attention to the fact that total problems can have more than 2 parts. They could have 3, 4, even 5 parts. And so here's an example of one of those problems. It says the animal park has 12 zebras, 25 monkeys, and some giraffes. If the total number of animals is 50, how many giraffes are there? And so all we have to do for our total equation is add plus P3 so that we have a space for all 3 of the parts in this total problem. And then in the chat, what is unknown in this total problem? One of the parts, again, absolutely. Absolutely, thank you. All right, so now we'll move on to our second schema, difference problems. And difference problems are when we compare 2 amounts for a difference, okay? So our difference equation is G minus L equals D. G stands for the greater amount, L stands for the lesser amount, and D stands for the difference. And so our graphic organizer has a longer bar for the greater amount, a shorter bar for the lesser amount, and then it has that space that represents the difference between those 2 amounts. And so our gesture for difference problems is we have a hand that is higher and we have a hand that is lower, and we ask are 2 amounts compared for a difference. So let's look at some star examples. This word problem says Gabby sent 2 boxes in the mail. The first box had a weight of 4 pounds, 1 ounce. The second box had a weight of 1 pound, 9 ounces. What is the difference between the weights of the 2 boxes in pounds and in ounces? And so in this example, we have the greater amount, we have the lesser amount, we have to subtract them to find the difference in weights of the 2 boxes. But for this difference problem, it's a little bit different. It says, and it's a mouthful, it says in November, 92,721 people went to football games in a stadium. That number was 14,629 greater than the number of people who went to football games in the same stadium in October. How many people went to football games in that stadium in October? And so in difference problems, the difference can be unknown, or the greater amount or the lesser amount can be unknown. So personally, when I taught second grade, as far as difference problems go, I had a lot of success using the graphic organizer. I had students draw the box for the greater amount. I had students draw the box for the lesser amount. I had them label what in the story was greater and what in the story was less. And then they used the graphic organizer as a guide to solve. So another quick review. Remember, we've gone over 2 of our additive schemas so far: total problems, where parts are put together into a total, and difference problems where 2 amounts are compared for a difference. So now let's walk through how to solve a difference problem using our difference equation. First, we'll write our attack strategy. And remember, 2 things about an attack strategy. The first step should always be to read the problem. And you also want to make sure that with your students, you're always using the same attack strategy. You don't want to use UPS check one day and then cubes the next. Stick with one attack strategy and make sure that you're using it consistently throughout the year. And within this presentation, we're using UPS check. So let's read the problem and understand it and underline the label. This problem says Jana has 107 wooden beads and 68 glass beads. How many more wooden beads than glass beads does Jana have? So our label answer is wooden beads because we're figuring out how many more wooden beads are there than glass beads. So we can check that step off, and now we'll move on to plan. So we know this is a difference problem because we're comparing 2 amounts for a difference. So our difference equation is G for the greater amount minus L for the lesser amount equals our difference. And in this story, we are solving for the difference. And so we can use the letter B as a placeholder for the number of beads. We know that Jana had a greater amount of wooden beads, 107, and a lesser amount of glass beads, 68 glass beads. And now we'll write our signs, and we need to subtract to find the difference between those two amounts. So the difference is 39 more wooden beads. Jana has 39 more wooden beads than glass beads. And when we check our answer and assess for reasonableness, we're going to make sure that 68 plus 39 equals 107. So one way to have students check their work is when I was in the classroom, I said, do all of the numbers fit together? With their reciprocal relationships. And so in this example, they do. 107 minus 68 equals 39, and 68 plus 39 more beads equals the 107 wooden beads. All right, so now I'm going to turn it all over to you guys, and I want you to solve using your printable. This word problem says, Farmer Hank has 6 more cows than horses. He has 4 horses. He also has 9 chickens. How many cows does he have? So take a few minutes to solve. So our label answer for this problem is how many cows does he have? So we will underline cows and check off the U for understand and underline the label. You see, we have also crossed out 9 chickens because that is irrelevant information. This word problem is asking us to compare cows and horses, not chickens. All right, so to plan, we will write our difference equation, G minus L equals D. And in this story, it says that Farmer Hank has 6 more cows than horses. And so that's referring to our difference. So we have 6 underneath the D for difference. We are trying to determine the greater amount because we know that Farmer Hank has a greater amount of cows than horses, and our question sentence is asking us how many cows does he have. We do know the lesser amount of horses, which is 4 horses, and so our equation to solve will be what amount minus 4 equals 6. And so to solve for this unknown, our missing value would be 10 because 10 minus 4 equals 6. And we'll want to check our work by solving to make sure 10 minus 4 does equal 6. All right. So moving on to our third additive schema, and that is a change problem. Change problems are problems in which you have a starting amount that increases or decreases to a new amount. And when I was in the classroom, my students would sometimes get confused between total problems and change problems. And so one key difference that I would always point out to them is that in change problems, there's some kind of action that is occurring that changes the amount in the story, okay? So we ask, does a starting amount, and we have our hand in front of us like this, increase or decrease to a new amount? And students will use the change equations, ST plus C equals E, or if there's a decrease, ST minus C equals E. And in this equation, ST stands for the starting amount, C stands for the change amount, and E stands for our end amount. So we see we also have our graphic organizer where we have the start, the change, and then the end amount. All right, so here's a star example, and it says, John put a pie in the oven at 5:15 p.m. He took the pie out of the oven 35 minutes later. At what time did John take the pie out of the oven? So John put the pie in the oven at 5:15, and then the time increased by 35 minutes. We are determining what time John took the pie out of the oven. And here's another star example. Landon had one string that was 10 meters long. He used 6 275 thousandths meters of this string for a project. So the action here is that he used it. He cut it off. He used it for a project. He took it away. And then the question asks, what was the length of string in meters that Landon had left? So our three additive schemas are total problems, where parts are put together into a total, difference problems where two amounts are compared for a difference, and change problems where a starting amount increases or decreases to a new amount. So to solve this change problem, we will write our attack strategy and read the word problem. This one says, a bus had 13 passengers. At the next stop, more passengers got on the bus. Now there are 28 passengers. How many passengers got on the bus? So our label is passengers. We want to determine how many passengers got on the bus at that next stop, because the word problem only tells us more passengers got on the bus, not exactly how many. So our plan will be our change equation, ST plus C equals E, because there was an increase. More passengers got on the bus. So now our starting amount is the 13 passengers that were on the bus to start. Our change amount is unknown, and our end amount is 28. So our equation that we will use to solve for the unknown is 13 plus blank equals 28. So to solve, students could either determine what they need to add to 13 to have a sum of 28, or they can subtract 28 minus 13. And so our answer here is 15 passengers. And then to walk students through reasonableness, you would just talk them through the story again. If the bus had 13 passengers to start and then 15 more passengers got on, would there be 28 passengers at the end of the story? Yes. And so our answer makes sense. 13 plus 15 equals 28. All right. So now off to y'all. This change problem says Martina had some money. Then she spent $42 on a sweater. Now she has $13. How much money did she have to start with? So take a few minutes to solve. So we are determining how much money she had to start with. In our change equation, it's a change decrease. So our change equation is ST minus C equals E. We do not know the starting amount because it just said that Martina had some money. And then we know that the change is that she spent $42. And then lastly, it says now she has $13. So that's the end amount. So our equation to match the word problem is blank minus 42 equals 13. So students have to solve for that starting amount. And so students can add 13 plus 42 to find that missing amount, which comes out to $55. And so to check for reasonableness, if Martina had $55 at the beginning of the story and then spent $42 on the sweater, then she would need to have $13 left. So to double check our work, 55 minus 42 does equal 13. All right. And then some change problems we like to call double change problems. And here's an example. It says Mrs. Lanier saved $617 in January. In February, she spent $249 of the money she saved. She saved $291 more in March. How much money had Mrs. Lanier saved by the end of March? So our change equation for this problem, we have two changes, ST minus C plus C equals our end amount. Our two multiplicative schemas are equal groups and set or comparison. And in equal groups problems, those are problems where we have groups with an equal number in each group, or we have a product that is shared equally among groups. And set or comparison problems are when we have a set that is being compared a number of times. So for example, I have 3 cups of coffee. Kate has 3 times as many cups of coffee as I have. That would be an example of a set or comparison scenario. All right, so our equal groups schemas. What is an equal groups problem? Equal groups problems are those in which we have groups with an equal number in each group. We have our graphic organizer and we have our equal groups equation, which is GR times N equals P. GR stands for the number of groups, N stands for the number in each group, and P stands for the product. So let's look at a couple examples from STAR. This example says, Jake has 24 tracks for his model train set. Each track has a length of 15 centimeters. What is the total length of the 24 train tracks in centimeters? So the groups are the number of tracks. The number in each group is the length of each of the track. And so we are going to have to multiply the 24 tracks by the length of each track to find the product or the total length of the 24 tracks in centimeters. This example says each of the 4 members of a team ran the same distance in a race. The members ran a combined distance of 7,500 feet. How many feet of the combined distance did each member run? So in this equal groups problem, we know the product, 7,500 feet. We know the number of groups, the 4 members of the team. We have to figure out the number of feet or the distance that each member ran individually. So those are 2 STAR examples of equal groups problems. All right, so this word problem says, Miss Thompson sold 6 cartons of cherries at the farmer's market. Each carton holds 25 cherries. How many cherries did she sell? So we will write our equal groups equation. We will underline cherries as our label answer. And GR stands for the number of groups. N stands for the number in each group, and P stands for our product. And so in this story, we have 6 cartons of cherries. Those are our groups. The number in each group are the 25 cherries in each of the cartons, and we're solving to find the product. And so our equation is 6 times 25, which equals 150 cherries. So now we can check off the S for solve, and we can move on to checking our work and checking for reasonableness. So 6 times 25 does equal 150. Our answer is correct, and we can move on. And so now you are going to solve an equal groups problem using our equal groups equation, GR times N equals P. This problem says Jane planted 24 tulips in her flower garden. She planted 6 equal rows of tulips. How many tulips were in each row? So when you write your equal groups equation, the 24 tulips is our product, the 6 equal rows is our number of groups, and we're trying to determine the number of tulips in each of those groups or each of those rows. We have our equal groups equation written down. We know that our product is the 24 tulips. We know that they were planted in 6 equal rows, and so that is our 6 groups. What's unknown is the number of tulips that are in each of those rows. So 6 times our unknown amount equals 24. And so we're solving for 4 tulips. And we can double check by making sure that 6 times 4 does equal 24. And to check for reasonableness in the context of the story, we can ask students, if Jane planted 6 rows with 4 tulips in each row, would there be 24 tulips in her flower garden? And if the answer is reasonable, which it is in this case, you are good to go. All right. So let's look at our last schema for today. And this schema is set/comparison. And set or comparison problems are problems in which a set is compared a number of times. And so we have our equation S times T equals P, where S stands for the set, T stands for the times that it is compared or multiplied, and P stands for the product. So let's look at a star example. The star example says, Jordan and Elizabeth are comparing the masses of their rocks. Jonathan's rock has a mass of 2/10 kilogram. Elizabeth's rock has a mass 8 times the mass of Jonathan's rock. What is the mass of Elizabeth's rock in kilograms? And so this is a star example of a set or comparison problem, where our set is the mass of Jonathan's rock, 2/10 kilogram, and the number of times we're comparing it is the 8 times, and we have to solve to figure out 2/10 times 8 to find the product or the mass of Elizabeth's rock in kilograms. So to review, our two multiplicative schemas that we covered today are equal groups, where students can ask, are there groups with an equal number in each group? And we have our set or comparison problems, in which students can ask, is a set compared a number of times? So let's walk through how to solve a set or comparison problem. This problem says, Isabella has 2 times as many chocolates as Emma. Emma has 6 chocolates. How many chocolates does Isabella have? So we are determining how many chocolates Isabella has. So we will underline chocolates as our label answer. We have red and we understand the problem, so we can check off the U. Now we'll move on to the plan. In this case, maybe we will use our graphic organizer to solve. We know that the product is unknown. Emma has 6 chocolates, which is our set, and Isabella has 2 times as many chocolates as Emma. And so our multiplier is 2. So we would have to solve 6 times 2 to determine the number of chocolates that Isabella has. And so in this word problem, Isabella has 12 chocolates. All right. We can double check our work through the use of a number line. And we are correct. So this is an example of a set or comparison problem where a set is compared a number of times. So one tool that you guys have in your spiral tool belt as far as teaching schemas is concerned is our routine word problem sorting cards and sorting mat. So we have the directions for how to use this in your Spiral Educator notebook, and we also have a video that walks you through how to use this resource as well. And so the gist of it is that you sit down with a student or you sit down with a small group of students and you read a word problem, and students have to determine what schema or what problem type the word problem belongs in. And then you will put it on that place on the mat. And it's a really good opportunity to talk with kids about the word problem without the pressure of having to solve it. If it's a total problem, you can ask students questions like, how do you know it's a total problem? What are the parts in the story? What is unknown, the total or one of the parts? I do this sorting activity every day in the intervention that I do with 4th graders, and it's been really awesome seeing how practice with this sorting activity helps students better articulate their thinking regarding word problems. So together, I have my cute little animations. Together, we are going to do some of these sorting cards. So I'm going to read a word problem, and then in the chat, I want you to tell me what schema this word problem belongs in. So our first example is actually the one that we solved together. Jonathan and Elizabeth are comparing the masses of their rocks. Jonathan's rock has a mass of 0.2 kilograms. Elizabeth's rock has a mass 8 times the mass of Jonathan's rock. What is the mass of Elizabeth's rock in kilograms? So in the chat, what schema is this word problem? Set, comparison, absolutely. Set or compare, excellent. So we would put that on that section of our mat and then pull out another word problem. So this one says, Olivia has 2 gallons and 3 quarts of vanilla ice cream and 1 gallon and 2 quarts of chocolate ice cream left over from a party. What is the total number of gallons and quarts of ice cream that Olivia has left over? So in the chat, what schema is this word problem? So I'm seeing in the chat, I see some total and some difference. And what I think is so powerful about the sorting activity is you can talk and explain your thinking. And so in this problem, we have an amount of vanilla ice cream and we have an amount of chocolate ice cream, right? But what's key is the question sentence. And it asks us, what is the total number of gallons and quarts of ice cream that Olivia has left over? And so we have to combine the vanilla ice cream with the chocolate ice cream, which would make it a total problem. However, and this is what I always say with students who guessed a different schema, if we change the question sentence a bit, it could fall into the difference schema category. If we asked how many more gallons and quarts of vanilla ice cream were left over compared to chocolate ice cream, that would cause it to fall into the difference schema. So I always tell students to pay extra attention to the question sentence, because what is unknown in the story, what is requested of you in order to solve the word problem, is going to be a really great clue as to what schema the word problem belongs to. And so that was a total problem. This word problem says Kelsey spends $6.75 every Saturday for breakfast. What is the total amount of money Kelsey spends on breakfast for 14 Saturdays? So what schema is this one? Absolutely equal groups. And a lot of students here would say total because it has the word total in it. And that's why we don't want to use keywords. We want to have a conceptual understanding of word problems in their totality. And so we know that we have to multiply. We have 14 Saturdays or 14 groups, and she spent $6.75 on each of those Saturdays. And so we have to multiply the groups by the number in each group to find the product. And so this is an equal groups problem. All right, how about this one? This is also one that we modeled. It says, Landon had 1 string that was 10 meters long. He used 6 275,000 meters of this string for a project. What was the length of string in meters that Landon had left? So change, yep. So he started out with 10 meters of string, and then he used some for a project. And so his amount of string that he had decreased after he used some for his project. So that is a change problem. How about this one? Zeke used 3/4 cup of white sugar, 3/4 cup of brown sugar, and 2 1/4 cups of flour to bake some cookies. What was the difference between the amount of flour and the combined amount of sugar Zeke used? And so this one's tricky because it does include difference. And I also did not point out to y'all that this mat has a multi-step category, and we haven't been able to talk about multi-step problems yet today. And so this is a multi-step problem, and it does include the difference schema. This multi-step problem has the total schema and the different schema. We have to combine the white sugar and the brown sugar into the total amount of sugar, and then we have to compare it with the amount of flour. And so this is a multi-step problem that includes the schema's total and difference. And y'all, this takes practice. Like, this is the first day that we've gone over schemas. It takes a minute to wrap your head around it. And so I really appreciate you guys. All right. Lastly, we have Hannah drew straight lines on her driveway with chalk. The table shows the lengths of the lines. What is the difference in meters between the lengths of line S and the length of line P? So what schema does this word problem belong to? Difference. Yep. We are comparing two amounts for a difference. And I really appreciate you guys for participating in the chat, like a lot. Thank you. All right, so that was our sorting activity. And now we're going to listen to Kate talk about our gestures.
Hi, my name is Kate Berry from the University of Texas at Austin. Welcome to this Math Spiral video. In this video, I will demonstrate how to gesture using schemas. When we think about word problems and setting up and solving word problems for students, we like to think about 5 different schemas at grades 4 and 5. We have total, difference, change, equal groups, and set and comparison schema. Our 3 additive schemas are total, difference, and change. When I say additive schema, all I mean is that students are adding or subtracting to solve the word problem. Our 2 multiplicative schemas, equal groups and set, are comparison, are problems or schemas that are used where students are multiplying and dividing to find the answer. We have found that when we ask questions and gesture, it's really helpful for students as they work through a word problem. So we have created some questions and gestures for each of these 5 schemas. Let's first take a look at our total schema. In total problems, we put parts together for a total. So our total gesture looks like this. Are we putting parts together for a total? So I put my hands out and bring them together. Are we putting parts together for a total? Now, I'm not going to say are we putting 2 parts together for a total, because we might have a word problem with 3 or even 4 parts. So to review, the total schema and question and gesture looks like this. Our parts put together for a total. Our second schema is difference problems. And in difference problems, we compare 2 amounts to find the difference. Our difference gesture looks like this. Are we comparing 2 amounts to find the difference? So we put one hand up here to show the amount that's greater, one hand right here below our chin to show the amount that's less, and we move the 2 amounts back and forth. So are we comparing 2 amounts to find the difference? For our third additive schema, or the change schema, these are problems where we have a start amount that either increases or decreases to a new amount. So our gesture looks like this. We put one hand behind our back and we say, do we have a start amount that increases or decreases to a new amount? I move my hand up to show the increase. I move my hand down to show the decrease. Students can also choose to think about change problems when we think about a number line. So instead of going up and down, we can move forward and back. So do I have a start amount that increases or decreases to a new amount? When we think about our first multiplicative schema, equal groups, this is when we have groups with an equal number in each group. So our equal groups schema gesture looks like this. Do we have groups with an equal number in each group? So I'm going to put my hand out to show the groups and my other hand inside to show the number in each group. So let's review. Do we have groups with an equal number in each group? The second multiplicative schema that we see in 4th and 5th grade is the set and comparison schema. And in a set or comparison problem, we have a set that's multiplied a number of times. So our gesture looks like this. Do we have a set that's multiplied a number of times? We can also think about like a bunny jumping forward. Do we have a set multiplied a number of times?
I just wanted to remind you guys that we didn't have time to cover multi-step problems today. But whenever you feel like you're ready to dive into solving multi-step word problems with schemas, we have resources for that too. And so this is a video that we have that models and talks you through how to solve multi-step word problems during schemas, and it's here for you whenever you're ready for it. So for our exit ticket, we have 3 questions that relate to feedback on this professional learning. And then we also have a set of questions that will be relayed back to your coach. I want you to think about the importance of using an attack strategy and teaching schemas. But on top of that overarching focus, you're going to be able to pick between 2 embedded focus areas. And that is implementing the sorting cards and the sorting mat that we showed you earlier, and gesturing. And so the idea is that everyone will focus largely on modeling the use of an attack strategy and teaching your students to solve word problems using schemas. But what are you going to put extra focus on? Either implementing the sorting cards and sorting mat or gesturing. And so, what is one way that you will collect student data related to your focus? If you choose to focus on implementing the sorting mat, you might mindfully pull sorting cards. Let's say you've only explicitly taught the total schemas so far. You'll pull some total cards, some difference cards, and some change cards, and then make a note of how well your students are able to identify the schemas of those word problems. If you focus on gesturing, maybe you'll have brief conferences with your students to document whether or not they know those gestures by memory themselves. And so you might ask them, what's a total problem? And then they might explain and they say, well, show me with your hands, what do we always do with total problems? And see whether or not they have made that connection between the schema and the gesture. So these are the 2 embedded focus areas that you will pick from, and I'm going to launch the poll. Prior to the next professional learning, which is either December 5th or December 6th, please gather examples of your students' computation errors prior to this professional learning, because we're going to be talking about error analysis, and you'll get a lot more out of your time if you have examples of your own students' computation errors that you can do error analysis on during that professional learning.